now we're looking at assignment 19, question 118. So in this question here, we're talking about a silver button battery used in a watch as zinc and silver involved. So now there's some form of zinc and silver. The bits of information you're getting right out of the first part of the question, that you're starting from 0.75 grams of zinc and it's going until 80% of the zinc is consumed. So this is telling you what's happening to the zinc. Zinc will be disappearing. So you know our zinc is being consumed and turned into something. We know in this case here, we've looked at many of these reactions, that zinc is oxidized, zinc 2+, and there's our balanced equation. That's our oxidation. That means that silver is going to be our reduction half reaction somehow. So in order to get the reduction of silver, it means that we're going to be generating silver. So we know silver is being generated. Starting from what? Generally an ion of silver, most common ion, silver plus. And we've seen many of these in class as well. And so in order to balance, we would have one electron. So if we want to completely balance and get the overall equation, we just have to multiply this one by 2. And then we can go through, cancel those guys out, and write out our full balanced equation. Okay, good. Now, other bits of information that we're learning from here is that we started with 0.75 grams of zinc, and we can go until 80% is consumed. So this is telling us our mass of zinc that's involved in the reaction. So a mass of zinc is going to be equal to 80% of 0.75 grams. So we have 0.6 grams of zinc involved in this reaction. So part A now is asking, how long can the battery run at a current 0.85 microamps? So here's our information, 0.85 microamps, which is equal to 0.85 times 10 to the minus 6 amps. Remember, that's our coulomb per second. So we want to find time. Our equation involving current, time, charge, T is going to be equal to Q over I. So we know our current, we need to find our charge here. And in this case here, we can get to there from moles of electrons. We don't know moles of electrons, but we can probably find moles of zinc from our mass of zinc. So that's the stage we're at right now. So in order to find our moles of zinc, we know our mass, molecular weight, so it's going to be our mass of zinc over our molecular weight, which is 65.39 for zinc. So after working this out, you should end up with 0.00918 moles of zinc. I want to convert this into electrons now, just doing our basic stoichiometry in this case here. So we're going to have, you just look at your balanced chemical equation, this one up here. So 1 mole of zinc for 2 moles of electrons. So we have 2 electrons over 1 zinc. So we're just multiplying this by 2. You're going to end up with 0.0184 moles of electrons. Now, to keep going with this one, probably fit it all down here actually. So remember, our time is equal to Q over I. Our Q, our charge, is a matter of the moles of electrons times the Faraday. So N for moles of electrons, or Z if you like, F over I. And you pretty much have all of these values now. You know your moles of electrons, you know Faraday's constant, you know your charge or your current in amps or coulombs per second. So you will get a time of 2.09 times 10 to the 9 seconds, which works out to many days, 2.4 times 10 to the 4 days. Now, if we go on to part B, let's keep that in mind because you do need that for one of the next questions. So I'm just going to erase, keep that up there. Okay, so part B asks, when battery dies, 95% of the silver oxide, so that's the form that the silver is present in, has been consumed. I'm just going to write that. 95% of that is consumed. Okay. What mass of silver was used to make the battery? So we want to find mass of silver total. Okay? So in order to do this question now, to get mass, we need moles of silver. Moles of silver, we need moles of electrons, and we have our balanced equation up here. So really similar to before, we know our moles of electrons. We had 0.0184 moles of electrons. And we know that those are equal 2 to 2. So that's going to equal our moles of silver. So for moles of silver, we can now find our mass of silver. Your mass is going to be equal to your moles times your molecular weight. And the molecular weight of silver, 107.87 grams per mole. So you will end up with a mass of silver. This is 1.98 grams. So that is how much is actually being generated in this equation. Well, of actual silver, and it actually doesn't make sense here. Anyway, it's all the same anyway, because this Ag2 plus is actually the Ag plus that we are looking at. I should be a little bit more specific in there, but it all comes from the same Ag because it's all 1 to 1. So 1.98 grams of silver is what is actually involved in this reaction. But we know that that's going until it's only, or 95% consumed. So this is only going to be 95% of the total silver that we have in the battery. So you know that then 1.98 over our total mass, that's 95%. So if we want to find our total mass of silver, then ends up being 2.09 grams of silver that's involved here. Now, for part C, this is kind of putting everything together, putting everything into perspective here a little bit. That. Okay, part C, if it costs now 27.48, this is dollars per 31.30 grams, which is a troy ounce. We want to know what the cost of silver consumed each day is for what's running here. So we can find our cost per gram of silver. This ends up being 0.878 dollars per gram. Sorry, it's like that. And also our other question is, well, how many grams of silver are we actually consuming or using up per day? So we know that we are using 1.98 grams of silver over a period of 2.4 times 10 to the 4 days. So if you work out this math here, we have 8.25 times 10 to the minus 5 grams per day. Putting everything together, multiply these guys together. And we're going to end up for a cost that is extremely small. So 7.24 times 10 to the minus $5 per day. And there's our final answer.